Hi everyone, today we're going to talk about applications of exponential and logarithmic functions. In a previous video, we have already seen example 1 where I collect some special kind of bacteria in a petri dish that starts off with 5 bacteria, and every minute the population of the bacteria doubles. So the function that we came up with was f of t equals, since we start out with 5 of them, we have equals 5 times 2 to the t power, and that 2 is because it doubles every minute. We also solved part B a different way, but now that we have the tool of logarithms, we can set our function equal to 1 million and then solve for t using logarithms. So I'm going to divide both sides by 5 here, and I will be left with 2 to the power of t equals 200,000. Now, the problem is that the variable that we are solving for is currently in the exponent. Now, before, we either had to use a table, a graph, or kind of guessing and checking. But now that we have logarithms, we can use the power rule for logarithms. So I'm going to use the common logarithm, but you're more than welcome to use the natural log or any base log you want, although most calculators only have a common logarithm or the natural logarithm. So I'm going to take the common logarithm of both sides. And we learned in a previous section the power rule for logarithms that says that if we're taking the log of something raised to a power, we can take that power on the outside and multiply it. Well, why does that help us? Why do we care about that? Now that our exponent, or the variable that we're solving for, is no longer in the exponent, now we can just divide both sides by log of 2 to get our variable by itself. And so t is approximately, I'm going to go ahead and throw that into my calculator. So I threw in log of 200,000 divided by log of 2, and I got that t is approximately 17.61 minutes, which is the same value that we got solving it last time using a different method. Okay, example 2 says in 1990, the estimated population of Pawnee, Indiana was 33,450. By 1991, the population had grown to 37,120. Assuming that the growth is linear, construct a linear equation that expresses the population P of Pawnee T years since 1990. If I were to create an input-output table where the input was the years since 1990, and then the output was the population. We know that in 1990, there was a population of 33,450, and the following year, the population was 37,120. Now, if we are assuming that this is linear, then we can use the slope formula that says m equals y2 minus y1 over x2 minus x1. So I'm going to call this one x1, this one x2, this one y1, and this one y2. So if I plug those values into my formula, then I get 37,120 minus 33,450 over 1 minus 0. And if I throw that into my calculator, I get 3,670. What does that number mean or represent in the context of this problem? That is the slope, and if we're assuming it's linear, that means that every year the population of Pawnee, Indiana is growing by 3,670 people. So our function will then be P of t equals 3,670t plus the starting amount of people in 1990, which was 33,450. So there is our linear function. Part B says, assuming that the growth is exponential, construct an exponential equation that expresses the population P of Pawnee t years since 1990. Now I'm going to refer back to this table that I created in part A. The difference, though, is for exponential functions, we are not adding the same amount every year. We are multiplying by the same amount every year. So to get from 33,450 to 37,120, I'm going to divide those numbers to see what I multiplied by. So I threw that into my calculator, and that was approximately 1.1097. I did round that to 4 decimal places. And so what that means is to get from here to here, we are multiplying by 1.1097. And if I wanted the population for the following year, I would go ahead and multiply by that same number again. So if I am creating my exponential function, then we would have our starting value, which was 33,450, times 1.1097 to the t power. Okay, so part C says use the functions that you created from parts A and B to estimate the population in the year 1997. So we are going to have 2 estimations, one if we use the linear function and one if we use the exponential function. All right, so for the linear portion, we want to evaluate P of, let's see, 1997 is 7 years after 1990. So that's going to be our t value. So P of 7 will equal 3,670 times 7 plus 33,450. And I threw that into my calculator and got 59,140 people. So according to our linear model, our population will be 59,140 people in the year 1997. And then let's see how much we are getting with our exponential model. So it would be P of 7, which is 33,450 times 1.1097 to the 7th power. And this one gives us a decimal, so I'm just going to round that. And that is 69,316 people. So those are our 2 estimations for the populations of Pawnee, Indiana in 1997. Okay, so example 3 says a population of flies on a remote island has 15,000 flies and grows by 7.2% each year. Okay, so part A says create an exponential function in the form p equals, I don't know why there's a box right there, but it should be p equals a times b to the t power that models the fly population after t years. So we know that the starting population is 15,000. And we know that it's growing by 7.2% each year. Now, if something is growing by a percentage, we call it an exponential growth model because it's growing. And I think in a previous video, I stated that if you have an exponential growth model of the form a times b to the t power, in order for there to be growth, our b value has to be greater than 1. And so that represents growth. And then decay is when it's decreasing, and that's when our b value is greater than 0, but less than 1. So if we were to change 7.2% into a decimal, that would be equivalent to 0.072. However, we know that it's growing, and so if we're growing by a percentage, what you want to do is you want to add 1 to it. So 1 plus 0.072 is 1.072, and then to the t power. So that is our exponential function that models this scenario. Now it says, how many years will it take for the phi population to reach 70,000? Just like we've done in a previous example, we can take our function and set it equal to 70,000. And now our goal is to solve for t. So I'm going to divide both sides by 15,000. And those will divide out on the left-hand side. So I'll be left with 1.072 to the t power is equal to 14 over 3. And again, you can use the natural log or the common log. I'm just going to use the common log. I'm going to take the common log of both sides. And then if I use the power rule for logarithms, the left-hand side now becomes this, where I've taken the exponent and am now multiplying it on the outside. Now, if I want to solve for t, I can divide both sides by log of 1.072. And so we get that t is equal to, if I throw that into my calculator, I will get about 22.16 years.